Yeah, back to the slides. Now everything appears. Yes, so you want two things. You want output functionality, so you ensure that you get Y, and also input privacy. So you do not learn more than what you could learn from the inputs and the outputs. And we consider a set of n parties and up to n-1 adversaries, which are public and static, which means they follow the protocols and try to learn as much as possible. And in fact, you can instantiate MPC with FHE by adding an access structure on top of FHE. This is meaning that you restrict who is able to decrypt what. And this is done with a key generation protocol, like Jay introduced to you, where you secret share the key among the participants. You generate some public evaluation key and public keys. Then you have an evaluation phase. And finally, you interact again to decrypt. So I will introduce now the ring learning error problem, which is the base construction on which all these schemes are based. And so we work in a polynomial ring of degree n-1 modulo q, and we need three distributions. We need a uniform distribution over this ring, a small error distribution, and a ternary distribution, and that's it. And essentially, the ring learning error problem is the distribution is defined as a small secret polynomial times a public uniform polynomial plus some error. And you have two hard problems on this lattice, which is a search problem. Essentially, you need to either find E or S, or the distinguishing problem, which asks you to distinguish a valid ring learning error sample from a uniform distribution. And from this, you can build homomorphic encryption. And this works because all operations are affine operations of the secret keys, meaning that if you apply an operation on a ciphertext, then it outputs a ciphertext on which the same operation will apply on a secret key. And it essentially preserves the structure of the ciphertext. So before and after the evaluation, all you need to do is have a secret key and multiply back the two components of the ciphertext to recover your message. And because all of these are affine of the secret key, there is one more thing to introduce, which is gadget. So, sorry. To encrypt the ciphertext, you simply sample a ring learning error sample, and you add the message on top of it. But sometimes you also want to multiply with a message, and for this you need another type of ciphertext, which is called gadget ring learning error. Essentially, it's the same as before, except you decompose your message with a base, and what this allows you to do is to do multiplication where the noise is independent of the message. And since all operations are affines of a secret key, then the setup phase, which generates the public encryption keys, is also affine of the secret keys. So all the elements in blue, they are linear operations over the secret keys, as well as the decryption and re-encryption, which is simply changing the secret keys. So these are all linear equations. And there is one issue with S square, but we will deal with it after. And this is great because now you can instantiate your protocols as public aggregatable transcripts. So since everything is a affine function of a secret key, then everything is additive. So each party can sample its own secret key locally, and then you do some protocol with public transcript, which output a sum of all the transcripts which correspond to a new transcript that is encrypted under the collective secret key, which is unknown by anyone, but each one knows a part of the secret key. So this is great because with that, you can instantiate a one-time setup, and it has a low round complexity compared to traditional MPC. You have 2 rounds for the setup. One of the 2 rounds is because of this really an instruction key which has an S square, which is not linear in S. Then the evaluation phase is completely non-interactive. This is why you have an overall low cost of communication. And you, again, need to interact for the decryption. And what this allows is completely delegated public share aggregation. And overall, it has a sublinear complexity multi-party computation. So these kind of schemes are implemented in the Latigo library, and it enables n out of n and t out of n threshold schemes. So this is a library that provides all the state-of-the-art FHE schemes. And it's also widely used, for example, for the Adash Privacy and Security Workshop, where this series was used by the two first-place competitors. But simply implementing these protocols is not enough, because you run into a lot of issues when you try to deploy them in practice. So Latigo has the construction and deployment of the base protocol, but when you run them in practice, then you run into some security issue and a client issue. For example, you need to make sure you have a reusable setup and that everything can be parallelizable, that the share for the key, which can be quite large in practice, can be supported by the client, so you need to share the shares. You need to support a predefined HE circuit evaluation, and also you need to ensure that if a client drops, for example, during the setup or at the decryption, you have some robustness, but also that it's still secure, even if you have these kinds of unexpected events. And for this, Helium was developed by Christian Mouchet, and this solves all these issues. So Helium is built on top of Latigo, and it provides a framework to be able to do FHE-based MPC and deploy practical solutions. So we have seen that we have a two-round setup. Basically, you need one round to generate the public key, and then one round to encrypt and generate the evaluation keys. But it would be great if we could have a one-round setup, because this would enable many more applications. So essentially, why do we have a two-round setup is because when we generate one of the public key, the revolution key, this key enables ciphertext compactness. So when you multiply two ciphertexts together, they do not grow in size. It depends on the public key, which itself depends on the previous protocol. So it would be great if we could reduce this to a single round. And the ideal framework would be that we have a set of predetermined parties. And each of these parties will send a single public aggregatable transcript to the server. And then the server can choose any subset of these parties, aggregates the path associated to these parties to generate the corresponding evaluation keys and ciphertext. He can run an arbitrary circuit. And then it only requires the collaboration of this subset of parties for the decryption. So back to the issue that prevents a two-round protocol. A one-round protocol. This is this rel interaction public key, which is an encryption of a square of a secret key. It's both important for ciphertext multiplication, but also for expanding some other kind of ciphertext which are used for the few bootstrappings, which is the scheme that is, for example, used as a backend in Phantom Zone. So if we look more at the structure of this key, then we see that it's a gadget RLWE ciphertext of the encryption of a secret key times the sum of all the secret keys. So it would be great if we could have a one-round protocol that is able to produce this kind of key-dependent message for both RLWE and GRW ciphertext. And, well, how can we achieve that? It's possible with some homomorphic operation. Basically, we generate from two RLWE ciphertext and one GRW ciphertext, you can hopefully generate this kind of key-dependent message RLWE ciphertext. And here, all the message, the FRMA secret key U, the error, the secret, etc., they are all affine, so they are all additive, which means each party can generate locally, non-interactively, and at the end, you can aggregate everything and get this encryption of the message times a secret. And this is great because now you have a solution to have this one-round protocol. And so we are back to our diagram, and now we solved this was a previous instance where we have one round for the public key generation, one round for the encryption, and the realization key generation. And this solves and changes it to one round for the key setup and one round for the encryption. This is already great. But allocating one round just for encryption is fine if we want to have dynamic and flexible on the secret inputs, but if the input circuit is fixed, for example, if you have a starting state, like for a game like Frog Zone or bank account, maybe you want to have everything into one round. And this is easily solvable. Basically, the party that wants to encrypt the message encrypts it under its secret, and the all other parties they have to generate encryption on 0 under their own secret. And you can aggregate everything, and this is equivalent to encrypting under the secret, the public key of the ideal secret key. The only issue is that it requires ON communication per ciphertext per party, meaning that for each ciphertext that a party wants to generate, all the other parties also need to generate a corresponding encryption of 0. And yeah, at the end, you could have a full one-round non-interactive setup with encryption if you want. So these protocols are not in the base library, but they are in my fork of the library, Latigo. It's a fork of Latigo that has over 30,000 change. It has new functionality, protocols, etc., like these non-interactive protocols. And there are also the backend of Phantom Zone, which is a Rust-based MPC focus library, which can evaluate arbitrary functions over a set of private or public inputs. And it has a high-level abstraction, which is focused for ease of use developers. And yeah, if you did not know it, it's the backend of the game Phantom Zone that is downstairs. And yeah, voila. Ah, yes, the questions. Yeah, I have to disconnect for the...
So we do have some live questions. You can sit here. So here we have one on the screen. Is this a best method than ZK proofs?
I would say it doesn't solve the same problem. It tries to ensure privacy. ZK proofs do not provide privacy. So FHE and ZK proof are complementary. You would use a ZK proof to, for example, right now, the server, you have to trust him that he will evaluate the correct circuit. And so what you get is a ciphertext which looks like random noise. How can you be sure that it's not a malicious ciphertext, which when you decrypt it will leak some information? So you would use ZK proof to have a proof that the server did evaluate the circuit it was asked to evaluate.
All right, we do have some extra time for QA, so let's wait for a few seconds to see if there are any other questions popping up. Oh, we have another one. What are the main differences between this library and the pre-existing ones, like Concrete?
Concrete primarily focus on TFHE, and the entire stack is built on this scheme. These libraries, they are more generic. They are, I would say, more low level. Also, they are not in the same language. So I would say first, if you want to use Rust, then use Concrete. But this Latigo, for example, provides support for the BGV, CKKS, which are schemes that enables vectorized arithmetic over complex number or finite fields. And TFHE is more like single gate arithmetic.
Awesome. And can you give some concrete use cases where one round protocol unlocks?
Yeah, so basically what it solves is liveness. Now you can just send your share and forget and go offline. You don't have to wait on the other parties to have some interaction to generate the setup and the ciphertext.
All right. Can you share any insights or number on the performance versus other libraries or protocols?
So multi-party FHE, what is essentially solved is the setup. The evaluation phase is the same as single-party FHE. And the setup remains, in most of the case, negligible to the evaluation of the circuit. So there isn't like concrete difference in practice.
All right. Are there examples to use your forked leticle with the features you mentioned in this presentation?
Yes, fork has a folder with examples, and there is an example that shows how to do a full one-round protocol for all the key that will be used in practice.
What resources would you recommend to learn about multi-party homomorphic encryption?
I would recommend to join the Discord of FHE.org. They have a lot of, it's a great community, and there are channels to learn and to discover, to ask questions, and there is always someone online, and they will point you toward the correct references if you have a specific questions.
All right, I guess the next question is also kind of related to the previous one. Are there any posts or publications where we can learn about these protocols?
Yeah, unfortunately, right now, no, it's only in the library, but we will submit something for the FHE.org conference, which will happen in March. The thing is that these are very simple and small protocols, even if they solve a problem that was not solved before. For question of time, we did not have the resource to produce something, but it will be there in a few months.
One last question. What are the challenges in this space we should look into?
Right now, I see two challenges that people face in practice. We have a lot of people that complain that the setup is heavy, like a few hundred megabytes to a few gigabytes, depending what you want to do. And depending on the circuit you want to run, the overhead can be quite large. So a lot of people say that FHE has 1 million to 1 billion times of overhead, but it's not really true. It depends really on the circuit you want to run. Some FHE circuits are as fast as plain text circuit, but they are very shallow. So it's use case basis. Personally, I look forward to having GPU or hardware acceleration for FHE. It will make things a lot more practical. But we had collaboration with people in the medical sector, and they said they did not care if it would take 3 weeks for the computation to finish because it took them 2 years to get the data, so it was nothing for them.
All right, so that's all the questions. Thank you guys so much for coming, and let's give another round of applause to Jean-Philippe. Thank you.